So hi everyone. In the previous video, we discussed about the data set. We did some preparation by creating CSV files, then dividing the data in train and test, then creating a small label data. Now in this video, we are going to create a data loader of all those data sets. So let's get started. So we already seen this step one of preparing this train test split and then preparing this test set and then preparing small label data. Now let's see how we can prepare a data loader that we can use it for uh, rendering the data for training or evaluation. So a few things that you have to know. So actually the files for the data loader is basically this flowers data set and data loaders. However, there are some other helper files that I will be showing you. So this is all the helper files are in this util submodule. So let's first see this function of computing mean and standard deviation. So what I'm doing here is simply I'm loading all the images and then I'm calculating the mean and standard deviation so that we can use it to normalize our data, like the mean normalization or any other normalization that you do. Now, one thing is the PyTorch to transform method. It converts the image to range 0 and 1. So I'm computing the mean and standard deviation in the range 0 to 1. But that's just this line of code. If you remove this, then you will get your mean and standard deviation in normal integer value, like between 0 to 255. But because I'm dividing it by 255, I'll be getting in the range of 0 and 1. So I'm just reading all the images from my flowers dataset category. I am looping over it, reading the images, then computing the mean and standard deviation. So now when we read the first image, we'll assign a mean and standard deviation variable, which will compute the mean and standard deviation. And from the first image onward, we'll simply append to this created variable. So np.append to this variable and then compute the mean over all the images. Okay. So if you run this, you will get mean as this and standard deviation as this. Okay. So this is one helper function that you can use to compute mean standard deviation. And another helper function that we'll be using is this one. So as I said, all my config file are in YML format. And usually when you have to access elements of a YML format, it's in the form of dictionary. Okay. And if you have to access a dictionary, you have to write the keyword. So let's take an example. I have a dictionary here, sample, whose name Anuj, subject AI. So if you have to access a dictionary, I have to use a keyword of say name and then it gives Anuj. What if I want to access in like object dot notation? That becomes more easier and intuitive. So sample dot name. So that is not supported by dict. So we'll use this helper function to help us do that. So what we can do, simply say sample object and we call this class of dot dict and pass our sample or the dictionary, and then now we can, if you see here, now we can simply access my keys with dot notation. Oh sorry, it's sample object dot name, and you can see it's coming as Anuj. So this helper function will be used to convert the dictionary into a dot notation. This is taken from this Stack Overflow. And the load YML file will load the YML file. Now you can give the option of whether you want to load in dictionary mode or a object mode. And the difference is just that it will call this class. Then I have a function to save the config files, save the YML files to the locations that you pass into, and it will simply dump it. So for now, only these three helper functions are helpful. Later, we'll discuss the other helper functions. And then there is this transformations.py. So basically, this is the function to rotate our image because we'll be preparing a data loader that has the rotated image, by varying degree 90, 180, 270, 120. So we have this helper function. One more helper function is this visualize. So where you simply pass your input data and labels, and you can plot the images and the corresponding labels like this. I think here I showed you in this EDA. So it's good that when you prepare a data loader, you just see whether it's behaving the way you intended to behave. So like this. Okay, cool. So here are okay, two things. One is that if the length of the input array is 4 means the images will be format of say number of batch size 12, channels, and then row and column. Okay, so this will not do anything. But if there is just one image, I mean there is no batch size, then it will expand as 1 3 128, and then we'll loop over all the images, and this will basically roll the axis. So the format which we visualize the image is row, column, and channel. So this will rotate the third axis here, and basically it does the plotting of the images. So once we are okay, discuss the utils or the helper function. Now let's come to the config. So this config SL I am defining for config supervised learning. This is the YML file, and the way you write entities in YML file is basically you write the variable name, a colon, and the value, and you can define lists and dictionary as well here in this format. So this is the list, this is the dictionary, and then I am giving the root path of data, the data path, the experiment type, which will be supervised for me. So if you remember, I'm storing in a supervised, like whatever nature of experiment I'm doing, I'm storing in that respective folder. Then the directory will be this which name you want to save it. So say experiment 100, then the image directory, the labels directory, and this is the log file. Again, as of now, we don't need to know it. Yeah, this is one thing. So the pretext task, so either you can make it false or you can make it Rotnet. But again, I think this is for supervised. For self-supervised, I'm sorry, for self-supervised, I've already added that pretext would be rotation, number of rotation 4. So use this file, it comes very handy. Like there's one place only where you have to define all your parameters, and you need not worry about defining it anywhere else. Now let's come to this, the main data loader. So here there are two scripts. Let's first see the flowers dataset.py. So what it does. So it's pretty intuitive, pretty easy, and no need to worry about. I'll just explain it. Let me zoom in a bit. So these are all the imports that I am doing, and basically I am defining a class. So if you have created a data loader in PyTorch, it follows a common structure. We'll be having a class which inherits from the dataset module. We'll have initialization, and then we'll have length and get item to return us the data. But there are a few things that I've added here so that we can modify our images to include rotations, etc. Okay. So this is pretty simple. So we have this class, we'll have a constructor where we'll initialize the configuration, the config file, the YML file that I just showed you. And then we'll have this annotation file, data type, and transform, like any transformation you want to apply to the data set. So what I have is a data path, basically the root path, data path, image directory will form the data path to our flower directory. Then the label path. So if you remember, we prepared the annotation file and path to this annotation, and then the transform. And this is self.pretext if we are defining any pretext task like rotation or maybe later simclr. And if the pretext task is rotation, the number of rotation is taken from the config file that we defined here. So config SSL, if you see the number of rotations, so it will be taken from here. So that's what maintaining this config file like YML gets really handy. You need not define everything again and again, just one place you need to define. And then what it does, once it gets initialized, it will call this load data function. And what is this load data doing is basically it reads the CSV file, the annotation file with the pandas. Then I create an empty loaded data list, and then I loop over all the first I'll get the length of this total number of images in this annotation file. Then I'll loop over one by one. And if you remember the config file, the annotation file that we saved, the image name was saved in file name header, and the labels were saved in label header. So I'll get the image name and label of that specific number, like ith element, and then I'll open it with PIL image library, and I'll simply append the image, the red image, the array, the label, and the image name. Image name will be coming handy in later use if you want to know which image file this array belongs to, and you want to debug or visualize. And then I'm simply appending it to the list. Okay, so this list will get totally filled up with the total number of samples. Then this image.load, actually why I'm using this is I was getting too many open file error when it was reading too many files, and this helps to close that. Then the length basically returns the number of elements that is there in the data set. So length of self-offloaded data. So self-offloaded data is a list containing all the arrays, the labels and the image name, and this will just return the number of samples in the data set. Then this is the main function that returns the item whenever the data loader is called. So this IDX is simply taking the IDX modulus length of self-offloaded data, so that if your ID is above the number of samples, then it gets repeated. Like suppose if you have 10 samples, uh, and if 10 number of samples and you call 15th index, then instead of 15 the fifth will be called. Okay, so from the loaded data, the whatever ID index is called, that index will simply take the image label and the image name. Now since we have to modify the input for the RotationNet, so I have additional function called read data where I pass the image and label, and then this will return the appropriate image and label. So if it's normal like Mendelian rows and all, the label will be 0, 1, 2, 3, 4 because there are 5 classes. But if I define number of rotation as 3 for the self-supervised task, then the number of labels should be 3, 0, 1 and 2. So this read data will do that. So what this function does is if the pretext task is rotation, and if the number of rotation is equal to 4, then it will take this image, one image that is passed to it, and that image it will transform it into four copies. So one will be 0 degree, one will be 90, one will be 180, and one will be 270. And then it will reassign the labels to 0, 1, 2, 3. If the number of rotation are 3, then it will give 0, 120, 240 and assign the label to 0, 1, 2. And then it will kind of append all these transformed images instead of, so like the final output will be in the form of 4 comma 3 comma 128 comma 128. Okay, so this will just stack all the image into one array, and this will return it. And if there is no pretext task, then it will simply apply any transformation that you define. Like if you want to do some kind of data augmentation like cropping or color change, then it will do that and it will return that transformed image. So then you will get this image label, and this transformed image and label along with the index of which it was called and the image name of it, it will be transferred back to the function it was called. Okay, so I'm so basically in we'll see people return only image and label. I'm also returning indexes and image name because yeah, I like to check which arrays belong to which image name and so on. So this is your main class for reading the data set. And once you have done it, then there is one additional function that I'm defining, a collate function. So basically in PyTorch, when you call a data loader, and if there are say 100 samples, okay, and each 100 samples are of the shape 100 comma 3 comma 128 comma 128. So my console is on the right side. So when you call a data loader, you even give a batch size. Suppose if you give a batch size of 10, then the data loader will return the data in the format of 10 by 10 by 3 by 128 by 128. Okay, yeah, I mean there will be 10 batches, and each batches will be having 10, 3, 128, 128. So the data loader does that automatically, and that is done by this default collate function. But when we are using this RotationNet, something changes, because if you give the batch size of 10, okay, then the for each sample of batch size, the number should have been written 10 by 3 by 128 by 120. This is the normal case. Like one batch of data. But now since each image is rotated 4 times, if you've been using the default Collate, it will be giving 10 by 4 by 3 by 128 by 128. But what we need for our training is not this, because every rotation has its own label. What we need is basically 40 by 3 by 128 by 128. Okay, so this defined collate function will help us to achieve from here like to here, which we can directly use for training. Okay, so now we have defined, let me run this and we'll see how things are. Now this is the main function. Once we've defined the function, we'll be calling it. So the config file which I am giving, so first I'm just giving the supervised config just to show you how supervised data loader will look like and how this Rotnet data loader will look like. And I'm loading this YML file, and I will be loading it as an object format. And then these are some transformation that I'm defining. Again, this cfg.data augmentation will be taken from the config file. If you give that you want to use data, okay, I have not defined it here, I guess. Yeah, sorry, here. If you give data augmentation is true, or the function, then it will do it, or if it's false, it won't do it. So again, it will check if there is some data augmentation to be applied. Then it will also check whether you have to do mean normalization. And then it will, if we are doing this both, then it will do a compose transform function. And if you are not doing mean normalization, then it will simply resize to whatever size you define. I think I'm defining the size of 128. And then it will convert to 2 tensor and then it will just return it. And for the test transformation, you don't need any transformation. So I'm just defining explicitly. And again, as I said, if you're using a pretext task of rotation, then we'll not use the default collate function. We'll use a Rotnet collate function, and else we'll be using a default collate function. So I will show you, this first example will not use the default collate. So you will see how it looks like. So let me call this, let me run this part. So it will load the config file and all the function. Then the annotation file is small label data. I'll be reading from this annotation file rather than from, so I have this annotation file which I prepared, if you see. So I'm reading from small labeled data that we prepared like 15 minutes ago. Okay, now this is the class flower dataset which I'm calling, and I'll be creating an object dataset. I'm giving the configuration file, the annotation file, and data type. So this somehow, okay, it doesn't matter here, but yeah. And this is the transform. So let me just call this, execute this, and a dataset object is created on the right side. If you can see, can I zoom this? Okay, there's no option. Okay, now let's see the length of dataset. So there will be 400 samples. And you can see any of the samples by giving them the index, if you remember. And in the return, like I was returning image, label, index, and image name, and you can see the image name returned, and yeah, it will be the full path. The image will be the red image, which will be some array. Okay, and the label would be the label. Cool. Now, if you remember the helper function that I defined, helpers.visualize, we can simply call this. So if it's, I've just given an if else statement. So if it's a numpy array, it will not convert. If it's a torch, that will convert in numpy and then send it. So this is the image, one single image. Now, basically in this training and all, we need a data loader rather than just this. Data loader will fetch this entire data set in a form of batch, and then it will feed directly to the model. So here torch gives a function called data loader, module called data loader. So where I'll pass the data set which I have, and the batch size, the collate function. So here will be the default, and shuffle, whether I want to shuffle it or not. So I'll just run it. And if you remember, this data loader is kind of a generator function, and if you want to get its sample, it's like you have to give a next and then get one by one. You cannot see directly everything at once. So actually I have also made a tutorial series on this data generator, and then how to create data loader of different types. So you can go check it out. I think it will be useful for some of your works. And then I will have this next, and then the data shape, it would be in the form of batch size 10 common channels, and then okay, I think it's 100 by 100 somewhere I defined. Okay, we can forget it for now. Yeah, and these are the labels 0 1 2 4, maybe 3 is not here in this batch. And then this is their another interesting function called iSlice. So instead, if you want, rather, suppose if there are 10, can I get the length of data loader? Let me just check. Let me clear it. Length of my data loader. So it's 40 because there are, in each of the batch there are 10 samples, so 14 to 10 is 400. Now if you just want 4 batches rather than 40 batches, then you can use this iSlice. This is mainly used for testing your functions, because you don't need to load and run the code through entire 40 batches, but just through 4 batches we can do that. And if you so this will be also useful to you, the iSlice function. It will give you 4 batches of data. And now if you visualize this data, then you can clearly see that yeah, the labels are simply 0 1 2 3 4 corresponding to different flowers. Okay, they are not rotated. This is basically supervised data loader. Now let's do something. Let's load the self-supervised, or what we can do, we can simply, so that's the advantage of writing this config in this. So dot notation. So if cfg dot pretext, let's print it. So cfg dot pretext is false. Now what if I just assign cfg dot pretext, sorry, is equal to rotation. Okay, so now I have assigned this pretext to be rotation, and the values get updated. So I will simply call this one once again, and now it will be calling this Rotnet Collate function. And even this the data set that we create, there also there will be this indication going that we are calling for a Rotnet data loader, and we can print the data set and it will simply be 400. You can extract any of the sample, and yeah, you can visualize this, but let's not visualize one. Okay, let's visualize one sample. Let's see what's there. Yeah, so you see, for every sample in this data set, there will be 4 rotations created. Class 0, class 1 90 degree, class 2 180 degree, class 3 270 degree. And prior to this, we saw that there was just one image coming. Okay. Now we have to create a data loader, and we'll pass this data loader. And then let me clear this. And let's call this next to extract one sample of this data loader. And if you now print it, it will be 40 comma 3 comma 100 comma 100. So there are 10 samples in each batch. For each batch, for each image there are 4 rotations, so 10 into 4 is 40, and the labels are simply 0 1 2 3 0 1 2 3, because 0 degree 90 degree 180 degree 270 degree 0 90 and so on. Similarly, we can do this iSlice if you just want to see the 4 batches of data, and the labels would be again 0 1 2 3, and you can visualize it as well. Let's see what it gives. There will be 40 samples. It will take some time. Yeah, so 0 1 2 3. So there was one image, it was rotated to 0 degree 90 180 270. Then second image, again 0 90 180 270. Again third image. So for each image there are 4 rotations created, and the rotations are used as labels. Now the 0 degree is 0, the 90 degree is 1, the 180 is 2, and 270 is 3. Now hadn't we used this collate function, you see, so now the shape of the image is 40 by 3 by 100 by 100. So let me just change this to suppose I'm using a default collate function, and then I call my data loader. Now let's see what is the shape of your data. So it will be 10 by 4 by 3 by 100 by 100. So basically the labels are in form of, for each of the image, this shape is provided to us. But this won't fed into the model because the model takes the shape of number of images, channel, row, column. So that's why we use that collate function. So I think this is it from the data, creating this data loader script and the function. Now I have written one more script called dloaders.py, and that is basically a wrapper around this all this messy things that we have created, and get a clean way of just call one function and get all the data loaders of train, test, validation, rather than writing all this function. So when we do the training, we'll simply call that wrapper, and we'll get the data loader directly rather than defining everything ourselves. So let's see that this was the main script. I hope you get it. Then dloaders.py, what I am doing is basically I'm defining some additional wrapper function. So I will first import the flowers dataset from this script and the rotate or Rotnet collate function. Then I am defining wrapper of get data loader, get dataset. So if you want the data loader, you can call this function and you get all the three data loaders: train, validation, test. And if you just want the dataset, and you want to create your own data loader in that script where you're working, then you can call this get dataset. And what these loaders will do is basically what was defined in the main function. You will have your data augmentation defined here, the transform, the pretext task from the config file, and then the train data set. We don't have the validation data set, so it's none here. And test data set. Now, one interesting thing that this we can do is, suppose if we don't have this validation data set, then a portion of train data set can be used as a validation. So that is defined by this. Again, this is given in the configuration YML file. So if you want a split of the train data, you just give 0.2, 0.3 and so on. And what this will do is it will take the train data set, and then it will have the indexes of all the data set in the train data set, and then the number of the percentage of samples that you want for your validation. It will calculate that, and then it will shuffle all the train samples and randomly take that percentage of samples for your validation data loader. And this is done by the torch function subset random sampler. So you simply give train indices, validation indices, and you can create a train data loader, a validation data loader. And this validation data loader is coming from a percentage of data from the train data set. And if there is no validation split that not given, then simply it will have your train data loader. And if validation data is there, then a validation data loader, or else we'll give it none. And a test data loader is, I think, have I defined it somewhere? Oh yeah, here is the test data loader. And had I been just asking for the data set and not the data loader, then it will simply return this, and it will not return this data loaders. So that depends on your requirement. So that's it. And I can also check this here. So I simply call this config file, and then I simply call this. No need to create all those. Just when you're doing training, just call this line of function. And okay, I didn't run this. Okay, I have to run this one. And then when you call this, sorry, you will see that it will create a train loader, validation, and test loader, and give it to you directly. And you can see, if I just print the data shape from one of the data loader, it's the batch size I think was 2, so it's 2 by 3 by 100 by 100. So this is the data loader. So I think this is the really important part, of going from raw data up to the data loader. How we'll create some helper functions, some files, some classes, and then get to this part where we have this nicely created data loader which we can directly use for training. So that was quite exhaustive, too many concepts, and yeah, quite a long video, but I think it was necessary for you to understand what are the steps that goes behind preparing a data loader, and there were some tricks that I think you can use it for your other tasks as well. So in the next video, we have this data loader. In the next video, we'll jump into the training, and we'll actually train without using Rotnet, with Rotnet, and see the performances. So tune into the next video, and if you have learned something, then please like the video, share it, comment it, keep safe, remain healthy, happy, and keep learning and keep exploring neurons. Namaste.